far with significance testing, we have talked about writing hypotheses, your null hypothesis and your alternative hypothesis, and then using the p-value as evidence to draw some kind of conclusion about those hypotheses. So just kind of a quick reminder here, what if the speed limit on a road is supposed to be 60, so let's say that the mean is supposed to be 60 miles per hour for the cars that are driving on that road, but you put a radar sign up and you want to see if now the mean is less than that. Okay, so your null hypothesis would be that the mean is 60 because perhaps that's the speed limit. And your alternative hypothesis, now that the radar is there, you want to see if the mean is now less than 60 miles per hour. Okay, so what you would do as the statistician is you would go out and you would collect a sample of cars and you would see how fast those cars are going. So maybe you spend an hour of your day out there with a radar gun and you're measuring the speeds of these cars as they drive by. And that constitutes your sample. And let's say that our sample, the average was 57 miles per hour with a standard deviation of 8 miles per hour. Well, obviously here the mean of 57 is less than 60, but it's not that much lower. So we start to wonder, is that just a coincidence, or is that enough evidence to really conclude that the mean is now less than 60? And the way you decide if that's enough evidence or not is by calculating the z-score and ultimately finding the probability. And we said that when p is low, reject the hoe. Now what we're going to be talking about today is the exact same process that we've seen before, but we're going to come at this from a new angle. We're going to learn something called the t-distribution. So far, all of the problems that we've been looking at, we have been trying to determine some hypothesis about the mean of the entire population. But somehow, even though we're not sure about the mean of the entire population, we've known the population standard deviation. That's a little bit silly to assume that you know what the real standard deviation is for the entire population when you don't even know what the real mean is for the entire population. So the more realistic way of performing these significance tests is to use the sample standard deviation instead. Now, if you use data from a sample versus the entire population, there's going to be more variability, right? Because we know that every sample is going to be different from the one that came before it and different from the one that would come after it. So when you use the sample standard deviation to do some kind of significance test, you need to account for that extra variability by using the t-distribution. Now, t-distribution is going to fluctuate based on your sample size. In fact, it's defined by degrees of freedom. Degrees of freedom is just where you take your sample size minus 1. So you can see in red here, if I trace the red curve, when you have a very small sample size and a very small degrees of freedom, the distribution is going to be short in the middle and a little bit wider on the outside. So it has that extra variability to it. But as your sample size increases, you can see the one that is yellow here. As your sample size increases, it gets steeper in the middle, taller in the middle, and narrower on the outsides. In fact, you see that black dotted line there? When your degrees of freedom reaches 30, you're almost the exact same as the normal distribution. Okay, so for all practical purposes, the t-distribution looks just like the normal distribution. It just accounts for extra variability when you're relying on a standard deviation from your sample versus the entire population. Now, with the t-distribution, you will be using a new formula chart to look up something called critical values. It's extremely difficult to find an exact p-value that goes with a test statistic for a t-value. So we're going to be looking up things called critical values and computing what we refer to as the rejection region. It will make a difference if you have a one-sided test or two-sided test, right? A one-sided test would be where your alternative hypothesis, let me switch colors again. One-sided test would be where your alternative hypothesis is something like the mean is less than 5, or maybe you're trying to prove that the mean is greater than 5. In this situation, you would only be shading one side of your t-distribution, and if you use a significance level of 5%, all 5% would be on that one side, okay? And you would be finding basically just the cutoff where anything beyond that point, you would reject the null hypothesis. If you have a two-sided test, maybe you're trying to prove that the mean is not equal to 5, something like that. If you're doing not equal to, it could be either end, and the combined significance level is still 5%, but if you split that in half on either end, you're looking at 0.025 on each side. In this case, you would have two critical values, one negative and one positive on either end. And again, anything beyond that point would be too unusual to be a coincidence, and that is the point where you would reject the null hypothesis. Let's practice finding those critical values. So the first one here says find the critical value for a one-sided test with a sample size of 12 at a 5% significance level. So a one-sided test here, I'm going to only shade one side. A 5% significance level means that I'm looking at a probability here in this shaded area of 0.05. And the sample size of 12, well, if I look at the chart here, I see probability on the top. On the left-hand side, I see degrees of freedom. So my degrees of freedom is n minus 1. So in this case, 12 minus 1 is 11. So if I want to know where exactly that cutoff is that's associated with the probability of exactly 0.05, then I'm going to come over here to and 11 degrees of freedom, and I'm going to trace inward here. 0.05, 11 degrees of freedom gives me a critical value of 1.796. So my critical value, T crit, my critical value is 1.796. Okay, well, what if we had a two-sided test? So the second one down here says find a critical value for a two-sided test with a sample size of 17 at a 5% significance level. So two-sided test means that I'm going to be shading both sides here. And overall, I'm looking at a significance level of 5%, but I have to split that up evenly on either end. So 5% split in half is going to leave 0.025 on each side. So on my chart, I'm going to be looking at 0.025, and then degrees of freedom is my sample size minus 1. So 17 minus 1 is 16. So over here on my chart, I'm going to go to a probability of 0.025 with 16 degrees of freedom, and I'm going to trace inward, and it looks like that puts me right here, 2.120. So my T critical value is plus or minus 2.120. And the reason why I say plus or minus is you have two cutoffs here. You have one on the left-hand side, which would be negative 2.120, and you have one on the positive side, which would be positive 2.120. Okay, so let's put this whole process together and practice running some one-sample t-tests. Eldura manufactures batteries that the CEO claims will last an average of 300 hours under normal use. A researcher randomly selected 20 batteries from the production line and tested these batteries. The tested batteries had a mean lifespan of 270 hours with a standard deviation of 100. Do we have enough evidence to suggest that the claim overestimates the lifetime of this type of battery? So let's start, as always, with our hypotheses. Our null hypothesis is going to be what is originally thought to be true. So the CEO claims that the batteries last an average of 300 hours. So we're going to assume that he's telling the truth. We're going to assume that the mean really is 300 hours, but we're trying to see if there's enough evidence to suggest that the claim overestimates the lifetime of this type of battery. So we think maybe it's actually less than 300. So we're going to try to prove that the mean is less than 300. Okay, so we're going to find the critical value, which is just our cutoff point. This is a one-sided test, right? I am only trying to prove here that the mean is less than 300. So less than tells me I'm going to shade the left side of my graph. We are using a significance level of 0.05. Since this is only on one side, all 5% is on just this one side. Let's see, we also need to know our degrees of freedom to be able to look this up on the chart. It says we're looking at 20 batteries, so that's going to be 19 degrees of freedom. So I'm going on my chart right now. I'm looking at 0.05 with 19 degrees of freedom, and I see 1.729. 1.729, and actually I am on the left side of my graph, that lower end, so that's really a negative 1.729 that I'm looking at there. Okay, that is my cutoff. So that is the critical value there. This is the t-value that's associated with a probability of exactly 0.05. So the red shaded section here is a probability of exactly 0.05. Now I'm going to switch colors and we are going to calculate the test statistic. All right, so test statistic, very similar to calculating a z-score here. You're going to take what you observed. Well, we observed from our sample batteries that the mean was actually 270 hours minus what we expected it to be. It was supposed to be 300 hours. With a standard deviation of 100. So standard deviation, remember we have a sample of 20 batteries, so we really need to do 100 divided by the square root of 20. This is going to be our test statistic. Now the only reason we're doing t here is because that standard deviation was just from the sample of 20 batteries. That's the only distinction that you're making between choosing a t test statistic or a z test statistic, is based on where that standard deviation comes from. All right, so I'm getting a test statistic here of negative 1.34. So keep in mind on your graph, this is a normal curve. It's symmetric. You've got 0 in the middle. Our cutoff is down here at negative 1.729. I need to figure out where we land on this chart. So negative 1.34 is going to be pretty close to that cutoff, but not quite there yet. So as far as making a decision here, we know when P is low, reject the hoe. Well, what's our probability here? So remember the red shaded part? That probability is exactly 0.05. If I shade down in green, and I want to know the probability of this entire section here, if the red part is exactly 0.05, then I know the green part is going to be more than 0.05 because the area in green is larger than the area in red. So if the red section represents a probability of 0.05, then I know that green section is going to be even more than that. Okay, so as far as our conclusion goes here, our test statistic, which is the negative 1.34, falls outside the rejection region, which tells us that our p-value is greater than 0.05. Now we know when p is low, reject the hoe. So in this case, we fail to reject the null hypothesis, and all that means is that we cannot conclude that the average lifetime is less than 300 hours. So in this case, there is not enough evidence for us to reject the CEO's claim. We can't prove that he's lying. We can't prove that these batteries last longer, last less than what he says that they do. All right, let's try another example. The dean from UCLA is concerned that the students' GPA have changed dramatically in recent years. The graduating seniors' mean GPA over the last 5 years is 2.75. The dean randomly samples 30 seniors from the last graduating class and finds that their mean is 2.85 with a standard deviation of 0.15. All right, so we want to test this claim. So over the last 5 years, the mean has been 2.75. So you're going to assume that it's the same now as it has been. But the dean is concerned that the GPAs have changed dramatically. So what we're trying to prove here is that the mean is different than it used to be, so that it's not equal to 2.75. Okay, so we're going to run this test. It is a two-sided test, right, because it's not equal to, so we're not just trying to prove less than or greater than, we're trying to prove either direction. So when I draw my curve, I have to shade both sides, and if my significance level is 0.05, that's the total probability, so that really puts a probability of 0.025 on each side. Now I need to look up where this cutoff is on my t-chart, and I know that that's based on my sample size. I need my degrees of freedom here. Since we sampled 30 seniors, 30 minus 1 gives me 29 degrees of freedom. So I'm going to go look this up on my chart. I'm looking at 29 degrees of freedom and a tail probability of 0.025. 29 degrees of freedom, 0.025, that's 2.045. 2.045, and of course, the other side would be negative 2.045 because this is symmetric. All right, so that is plus or minus 2.045. That is our cutoff. If our test statistic falls in the shaded region, remember that shaded region is called the rejection region. If you land in the shaded area, you will reject the null hypothesis. All right, so test statistic here. So test statistic, just like a z-score, you're going to take what you observe in your sample, 2.85 for our mean, minus what you expected, which was 2.75, because we're assuming there's no difference, divided by our standard error, which would be our standard deviation, 0.15, over the square root of 30, since there were 30 people in our sample. All right, this gives me a test statistic here of 3.65, so that's going to be way up there on the positive side. This is going to be further down the line than 3.65. So think about what's shaded here, this part that's shaded in green. If the part shaded in red is a total of 0.05, a p-value of 0.05, the part shaded in green is much, much smaller than the part shaded in red. So I know that my p-value is less than 0.05, and when p is low, reject the hoe. So our conclusion would look something like this. Since our test statistic falls inside the rejection region, we know that the p-value is less than 0.05. And when p is low, we reject the null hypothesis. And if you reject, that means you have enough evidence. You can conclude that the students' grade point average have changed dramatically in recent years. So we know that they're different. Okay, so we just did this problem as a one sample t-test, and we were able to reject the null hypothesis and conclude that students' grade point averages have dramatically changed in recent years. So now I kind of want to follow up our analysis with a confidence interval. So we know that they've changed, but we don't know how much they've changed. We have no idea what exactly those grade point averages are looking like right now. So that's the purpose of our confidence interval, is to estimate what the true mean is now. So remember, on your formula chart, the formula for confidence interval is x bar plus or minus your t critical value times the standard error, which is just standard deviation over the square root of n. So we are going to build this thing up. X bar, also called your point estimate, is just the mean that you get from your sample. So in our sample of 30 seniors, the average GPA was 2.85. So we're going to start with that because that's our best guess as to what the true average GPA is now. But we know that that's not exactly right because that's just based on these 30 seniors. So we're going to build around that a margin of error. All right, to get our critical value we have to look up on our chart. 95% confidence interval. If I draw my curve, 95% confidence interval is going to be 95% in the middle, and of course if 95% is the middle, that leaves 0.025 on either end. And with a sample size of 30, that's going to be 29 degrees of freedom. So what I'm going to do is I'm going to go look this value up on my t-table. So I'm going to go to 29 degrees of freedom and 0.025 for the probability. That's 2.045. So obviously negative on this side, 0.045, and positive 2.045 on this side. That's my critical value. Times our standard error, and the standard error is going to be the standard deviation, 0.15, over the square root of our sample size. Now I'm going to bring this part down. This part right here all together is called the margin of error. So the margin of error, I'm typing this into my calculator, 2.045 times 0.15 over the square root of 30 is 0.056. That's the margin of error. And what that means is the kind of wiggle room around that point estimate. So we have a sample of people, their mean is 2.85, but we know that's probably not exactly what it is for all of the seniors that graduate from UCLA. So you calculate this margin of error, which gives you kind of some space around that point estimate so that you can get an interval to contain the true GPA. So on the lower end, if I subtract 2.85 minus 0.056, the lower boundary is 2.794. And if I add 0.056, my upper boundary is 2.906. So we are 95% confident that the true mean GPA for all graduating seniors is now between 2.794 and 2.906. So I can say with 95% confidence that the mean GPA has increased since the last 5 years. The average was 2.75. This entire interval is more than 2.75, so I know for sure that the average GPA has increased for graduating seniors at UCLA. All right, let's try another one sample T interval. A manufacturing process is designed to produce bolts with a 0.5-inch diameter. He selects a simple random sample of 25 bolts and calculates the average diameter to be 0.53 inches with a standard deviation of 0.2 inches. Construct a 95% confidence interval for the true average diameter of the bolts. All right, so we are going to do the same thing here. We're going to make a confidence interval. Our point estimate is what you found in your sample. In our sample, the average diameter was 0.53, so we're going to start with that, 0.53, plus or minus our critical value. Now this one we have to look up on the chart, so I'm going to draw a little picture over here. 95% confidence. When you do a 95% confidence interval, that 95% has to be in the middle, right? You're looking at the middle 95%. And if it's 95% in the center, that leaves a probability of 0.025 on the outsides. And we need to look this up on the chart. The other thing we need to know when we look it up on the chart is the degrees of freedom. So if we have a sample size of 25, that's going to be 24 degrees of freedom. So I'm going to go to my chart. I'm going to look up 24 degrees of freedom at a probability of 0.025. 24 degrees of freedom, 0.025, that's 2.064. 2.064. Okay, so that is my critical value, 2.064 times the standard error. And standard error is just going to be my standard deviation, 0.2, over the square root of our sample size. And we're just going to bust out the calculators here and go through and compute this interval. I'm going to start by calculating the margin of error. So I'm going to type this in all together here. 2.064 times 0.2 over the square root of 25 is 0.08256. That's our margin of error. So if I make my interval now, the low end, I'm going to subtract. The low end is 0.44744, And the upper end, if I add 0.53 plus 0.08256, I get 0.61256. So basically, how big are these bolts being produced? Well, we are 95% confident that the true diameter is somewhere between about 0.45 inches and 0.61 inches. So, does the machine need to be recalibrated? Well, remember, they're supposed to be ½ an inch in diameter. So, on the low end, maybe the bolts are being produced too low, and on the upper end, maybe the bolts are being produced too large. But you know what's in between those numbers? 0.5, so maybe they're being produced just right. So, does the machine need to be recalibrated? No. There is not enough evidence to say that the bolts are not being produced correctly. Maybe they're too small, maybe they're too big, or maybe they're just right. There's just not enough evidence to say that they're not the right size.